Hi everyone, Mrs. Hanson once again, picking up in a next new chapter. This chapter devotes its time to the study of chemical reactions. When we look at our topics of chapter 5, we'll begin by defining what is a chemical reaction and how do we use that to represent a chemical change. We'll learn how to balance chemical reactions and classify those types of reactions into patterns that we will study. Those patterns of chemical change fall under a larger category of oxidation and reduction. Section 5 introduces the mathematical concept, so kind of thinking about this part is more conceptual and recognizing patterns of chemical change and learning to balance equations. This is a very mathematical section, calculators out and ready, when we introduce the mathematics of how to read a balanced chemical equation in terms of moles, in terms of particles, and even in terms of recipes with stoichiometry. Stoichiometry is the heart of all of chemistry in terms of reading a balanced equation like you would a recipe card. The last little topics here, percent yield and limiting and excess reactants, are applications of the stoichiometry mole concept. So this is a very deep chapter. As much as I can tell you, they all are, and it will devote some time to just practice to become proficient with your skills. So we begin by writing and balancing chemical reactions. We learn to classify these reactions as combinations, decomposition, single replacement, or double replacement. We'll introduce the concept of redox reactions, oxidation as the loss of electrons, reduction as the gain of electrons. We'll pull out our calculators and start defining a term called mole, an Avogadro's number. We'll calculate the formula weight, which was commonly called the molar mass of a compound. How much do we weigh out to get one whole mole of a compound? That's what molar mass will mean. We'll relate the mass of a substance to its number in chemical moles. We'll carry out mole, and mass calculations, calculating percent yield along the way, and be able to determine if a limiting reactant is present in an equation. So a long journey ahead. Let's begin with taking our first steps. Notepacks out, here we go. An introduction to chemical reactions begin by reminding us that an equation is used to represent a chemical change. So let's go back from our very first chapter where we understood the difference between chemical and physical changes. Remember, a physical change alters a physical state of a substance, but it does not change the identity. It is exactly the same in chemical composition as it was before. Now, as an example, if we were to take water in the solid phase and allow it to melt to go to a liquid phase, notice that we have the exact same chemical identity. Water is on the left as H2O, water is on the right as H2O. So the same chemical identity on the left and the right, all that's happened is a phase change. The solid melted into the liquid water. A physical change, just as an example, would still have water molecules, 2 H's bonded to an oxygen, 2 H's bonded to an oxygen, and all we did was allow those water molecules to become, at a higher energy state. Notice that these are more randomly organized. The liquids have an ability to flow, and yet it is still the exact same chemical composition. And that's the clue. That's really the key for a physical change. Alters the physical state, but without changing the composition. On the opposite side of that would be a chemical change. A chemical change converts one substance into another. So we create new compounds. That the resulting products are very different in chemical and physical properties than what we started with. Chemical reactions involve breaking bonds in the reactant side and forming new bonds on the product side. Reactants are the starting materials. Products are the ending materials. The reactants break bonds. So we can see this definition. The reactants are the starting materials, and the products are the ending materials. We say things such as reactants yield products, reactants go to products, reactants form products, whatever you want for that arrow. A chemical reaction involves breaking bonds in the reactant side and forming new compounds on the product side. Let's take a very specific example. When I look at this molecular model, notice that inside of this reactants, I have a methane molecule, CH4. That methane molecule, I see 1, 2 of those. This unit, this little value here is going to be called a coefficient. It's telling us how many methane molecules are the starting materials. And do you see that molecular art gives us 2 molecules of methane? I also see, now see that plus sign? I also see 1, 2, 3, 4 molecules of molecular oxygen, O2. Notice these starting materials are what we call reactants. They're beginning materials. Then I see the arrow, and this means yields, forms, produces, goes to, makes, all kinds of different words to represent the reactants are going to change into something else. Well, what else do we see? On the product side, we see completely new compounds. I see carbon dioxide, 1, 2. Notice I'm going to put a 2 in front of a carbon dioxide to let you know there's 2 molecules of CO2 that formed. Then I see a plus to separate the 2 products, this and that, so a plus sign. And now I'm counting 1, 2, 3, 4 molecules of water. The ending products are very different in their chemical composition as the reactants. Reactants yield products. Notice the methane and oxygen converted into 2 completely new substances called carbon dioxide and water. And coefficients are used to balance a chemical equation, which we'll learn means to have the same number of each element on both sides. That's really obeying the law of conservation of mass, which we'll say is you cannot destroy matter or create matter. All you can do is convert it from one form to another. So we use coefficients to make sure we can account for all of the starting atoms on the product side. And so that's where we're counting each individual element. And we will practice balancing equations. Plenty of practice coming up. But now this skill is just trying to remember, is this a chemical change or a physical change? Can we represent these following reactions, or are they a physical process? So let's take a look at the molecular art in letter A. I have a molecule where 2 atoms of a blue, well, the blue atoms are bonded together to create diatomic molecules. And I have over here 2 molecules of a diatomic red atom, right? So 2 atoms of the red ball bonded together. So I could just say I have 2, and let's just use B to represent the blue, and there's two molecules of B2. And on this side, there's 2 molecules of a red atom bonded together to make a diatomic molecule. What else do we see over here? Well, now look, all of these have switched partners, haven't they? Now I have a blue bonded to a red. So I'm going to let that be represented by blue-red in terms of the molecular model. This indeed represents a chemical change because these bonds had to break. So these bonds over here were broken. I broke those guys apart. And that's the very definition of a chemical change. Bonds were broken, and over here, new bonds formed. Now let's take a look what we have here. Inside this molecular model, looks like we have a red, Looks like water, doesn't it? A red attached to two whites. That's a water molecule. And it looks like they're still just kind of in a liquid form, where I can see they're close together, but they're randomly displaced, right? So that would be in a liquid phase. And over here, it's the same structure where I have a oxygen bonded to two hydrogens, same compound, but now they're very far apart, which would represent the molecular phase of a gas. So really, we've just gone from liquid to a gaseous phase, which is a phase change. It would be called evaporation when a liquid converts to a gas. So this we would represent as a physical change. And this last one looks like it just became more ordered. So this would represent a liquid phase where the molecules are still close together but in a random order. And over here, this represents a solid phase where they still have the same atoms but very ordered. So when a liquid converts to a solid, that's called freezing. We could represent this also as a physical change. So the only chemical change with those molecular models was the first in letter A. So we've learned that a chemical reaction can be denoted through a chemical change. In this example, I see a molecule of H2O2. That's called hydrogen peroxide. It might be in your medicine cabinet at home, hydrogen peroxide. And I see that it undergoes a chemical change and it starts to bubble. Do you see in this hand, there are bubbles coming out, and that's evidence of something new. Now, peroxide will spontaneously decompose, and we're going to learn that decomposition is one of our 5 general patterns of chemical change. When hydrogen peroxide decomposes, you see that a water molecule is released, and it generates oxygen gas. And we'll learn that that little G is going to represent the gaseous phase. The AQ, we'll learn, will represent dissolved in water, aqueous. And we'll learn that the little L I've used here represents the liquid phase. We'll also learn that this equation is not yet balanced, and you'll hear me call those a skeleton equation. One that is completely written in terms of correct formulas on the left for the reactants. And I have the products over here on the right-hand side, but it's a skeleton because it's just not yet balanced. And when we learn how to balance equations, I'm going to model those with a T-chart. And for a T-chart, you'll hear me say, let's represent the left side and the right side of our arrow. The left side meaning the reactants and the right side meaning the products. And we have 2 elements we have to account for in this equation. We have H's and O's. And I just have to count. On the left side, I see a total of 2 hydrogens and I see a total of 2 oxygens. On the right side, the product side, I can count 2 hydrogens, but now a new combined total of 3 oxygens. 2 from the molecule O2 and 1 more from the molecule of water for 3 total atoms. So clearly you see it's not yet balanced because I can't just automatically invent another oxygen. It had to come from somewhere. So we'll learn that coefficients are going to be required to balance these. And when we learn to place a coefficient in front of a reactant or product, we have to retabulate every time we change a coefficient, because the coefficient of 2 distributes throughout the entire compound. It speaks to both the hydrogen and the oxygen. So now let's retally. Hydrogen, 2 molecules, each with 2 atoms of hydrogen, now gives me a total of 4 hydrogens. Same with the oxygen, 2 molecules, and each molecule has 2 O's. That's a total of 4 O's. And now when I recount, over here, I'm going to need to adjust the hydrogens. And so when I fix my T-chart, 2 times 2 is 4 oxygens, and we have 2 plus 2 more is 4 oxygens. So we've just balanced our first equation, representing all kinds of good vocabulary words. Reactants turn to products. The reactants are the starting materials. We write out what's called a coefficient in our balanced equation to help obey the law of conservation of mass. So this chemical equation uses chemical formulas and other symbols showing what reactants are the starting materials in a reaction and what products are formed. To define a chemical equation represents a chemical change. Reactants are written on the left. Reactants are the starting materials. The starting materials have their bonds broken as new materials form. The ending materials are known as the products, and the products are on the right side of our arrow. And we said these numbers that we place out front are called coefficients. The coefficients show the number of molecules of a given element or a compound. Coefficients are used to balance equations. They're used to obey the law of conservation of mass. Coefficients are these whole numbers written out front to tell us how many molecules, or we'll also learn to tell us how many moles are present. When I read this balanced equation, I see one molecule of CH4 reacts with 2 molecules of oxygen to form 1 molecule of carbon dioxide and 2 molecules of water. And do you see how I'm using the word molecule to represent the unit that a coefficient is giving us? How many molecules of each reactant and product are needed to balance the equation? That's the job of the coefficient. And we use these coefficients, we said, to obey the law of conservation of mass. And we're asked to define that term and just simply say atoms cannot be created nor destroyed in a chemical reaction. Atoms cannot be created nor destroyed. All we can do is rearrange them in terms of reactants turning to products. And that's the purpose of a coefficient, is in accounting. We want to account for all of the different atoms that we started with to make sure we end with the same number of each atom. So what does it mean to have a balanced equation? It means we have the same number of atoms of each element on both sides of our equation. Let's count together. In this example, let me just go through this with you. In this example, you have typed on your page, looks like this. CH4 plus 2 O2s yield CO2 and 2 H2O. We're being asked to just account how many atoms of each are present in the equation. And this is why I encourage you just to think about a left-right chart, a T-chart I call it. Notice we have 3 different elements we're counting. We have a carbon, we have a hydrogen, and we have an oxygen. C's, H's, and O's. The carbons are represented in red. I see 1 atom of carbon on the left, and I see 1 atom of carbon on the right. Notice the hydrogens are written in black. So here I see a total of 4 H's. And over here I see 2 molecules of H2O. Now think about what that means. It's like writing H2O twice. That's what the coefficient of 2 means. 2 groups of water. How many total hydrogens? Well, there's 2 in the first molecule plus 2 more in the second molecule for a total of 4 hydrogens. And now let's count oxygens. Here we have an oxygen molecule, but we have 2 of them. That's what the 2 in front of here means. 2 groups of O2. That gives me a total of 4 individual atoms. Here's a molecule with 2 oxygens. So that would be like writing carbon dioxide just once Each carbon dioxide has 2 atoms of oxygen. And remember, writing 2 groups of water gives me 2 more oxygens. So there's a total of 4 oxygen atoms. And that's what we tallied there. 1 carbon, check. 4 hydrogens, yes. 4 oxygens, yes. Since we have the same number of each element on both sides of our arrow, we know that we've obeyed the law of conservation of mass and that we've balanced our equation. Now, when we practice balancing equations, the skill here is to really understand how to count atoms. That's what we're practicing now to take a next step in deciding what coefficients we need as you're given an unbalanced equation. So the first step is to simply count. This is a pattern of chemical change where I see a hydrocarbon reacting with oxygen, forming carbon dioxide and water. We will learn that this type of chemical change is known as a combustion. Did you notice this was also a combustion on the previous slide? We had a hydrocarbon reacting with oxygen to form carbon dioxide and water. We have a hydrocarbon, which really is just a type of fuel that you burn in oxygen and you form carbon dioxide and water. It will be one of the 5 patterns of chemical change that we write about in our notes here shortly. Taking a fuel consisting of hydrogens and carbons and other elements such as an oxygen in this example and burning it. That's known as a combustion. Now let's count. Let's create a T-chart, and so we can tally how many atoms of each element there are on the left side of the arrow and on the right side of the arrow, reactants and products. There are 3 different elements present. I can count carbons, I count hydrogens, and I count oxygens. C, H's, and O's in this combustion example. So notice that the highlighter that I'm going to use is going to place a highlighted mark over what we call coefficients. And coefficients distribute through the entire compound. It's telling us how many of each molecule we have. These are very different than what we call subscripts. Subscripts set next to individual elements telling us how many atoms we have within the compound. Coefficients distribute through the entire compound. So when we count C2H6O, that is 1 molecule of C2H6O, and inside that molecule I count 2 individual carbon atoms. Inside this 1 molecule of C2H6O, I can see 6 individual hydrogen atoms. And I see 1 oxygen. I also have 3 groups of O2. It's like writing oxygen 3 times. Each individual molecule is composed of 2 oxygen atoms. So that's a total of 6 atoms of oxygen, plus the 1 more from this particular molecule gives me a total of 7 O's, 7 oxygens on the left-hand side. Let's do the same tallying on the right side. Here we have a coefficient of 2, which is communicating all the way through that molecule. Carbon dioxide, well, there's 2 of them there, so each individual carbon counts to 2. 2 times 2 is 4 for the oxygens, plus 3 more from the water, giving us a total of 7 oxygens. And 3 times 2 gives us a total of 6 in terms of the hydrogen. Can you visualize that? Visualize what these coefficients mean. We saw a coefficient of 1 in front of our molecule. Notice that's our fuel, our hydrocarbon that we are combusting. It contains 2 carbons, 6 hydrogens, and an oxygen. And to burn it, To ignite it, we had 1, 2, 3 molecules of oxygen. For every 1 molecule of the fuel, 3 molecules of oxygen were required. Now notice, bonds broke on the reactant side, and new bonds formed, creating new compounds. So the very definition of bonds breaking and new bonds forming is a chemical change. We had 2 molecules of CO2 form. We had 3 molecules of water, 3 H2Os. But when we're balancing equations, we're counting individual atoms. Let me model for you what I mean. Here's the 2 carbons right here. Here's the 2 carbons right here. Carbons are balanced. 1, 2, 3, 4, 5, 6, 7 oxygens. 1, 2, 3, 4, 5, 6, 7 oxygens. Perfect. And here we have 1, 2, 3, 4, 5, 6 hydrogens. And on this side, 1, 2, 3, 4, 5, 6 hydrogens. We have indeed balanced our equation. So coefficients allow us to obey the law of conservation of mass. We count individual atoms to make sure that there's the same number of each element on both sides. Coefficients tell us how many molecules we have of each reactant and each product. It's time for you to practice. Turn off the video for a moment and just count how many atoms of each element in these balanced equations, and then come back to me when ready to check. Welcome back. In letter A, this is a very familiar equation from a slide ago. This is the one that we were looking at where hydrogen peroxide decomposed. Notice I'm going to say this is a decomposition reaction, just so I can see a little bit of a lesson coming up. To decompose means I take a compound and break it into smaller pieces, right? To decompose, we have one reactant turning into more than one product, right? You're breaking it down into simpler pieces. So that pattern of chemical change we'll learn. Decomposition, what makes it unique is it has just one reactant breaking down into many products. We're just being asked to count in this example. There's 2 different elements to count. We have 2 groups of H2O2. So just thinking about what that means, 2 molecules of H2O2 that connect HOOH. So how many individual atoms did you count? There's 1, 2, 3, 4 hydrogens and 1, 2, 3, 4 oxygens. So on the left side, there's 4 of each atom. 2 times 2 is 4 for both of those atoms. Now let's consider the right side. We have a water molecule form, and there's 2 of them there. 2 H2Os, and we have an O written as an O2 molecule. So just kind of thinking about what balanced means. When I count, on the left side, I count 1, 2 oxygen atoms, and I count 1, 2, 3, 4 hydrogen atoms. Over here, 2 more oxygens. So let's tally up what we have. The number of H's, 1, 2, 3, 4. The number of oxygens, 1, 2, 3, 4. We have 4 atoms of each element. The reactants turn to products when we balance our equation. Same number of each atom, we've had a decomposition reaction occur. Let's look at letter B. I notice that I have a hydrocarbon. Hydrocarbon is an element composed of carbons and hydrogens. This would be called a fuel. It's an octane. Hear that oct for carbon 8? We see that it's being placed in with oxygen. Out comes carbon dioxide gas. And another product was called water. We are learning that this represents a pattern of chemical change known as a combustion reaction, where we'll learn when a hydrocarbon burns in oxygen, it releases carbon dioxide and water and a whole lot of heat energy. But now our skill is to practice counting. Let's create a T-chart that represents the left side of the arrow and the right side of the arrow. We have to count carbons, we count hydrogens, and we count oxygens. Those are the three different elements presented in our equation, C's, then H's, then O's. 2 to 25 to 16 to 18 is our coefficient ratio. That tells us how many individual molecules we have. Well, when I look at carbon has 2 groups, and there's 8 within each, so that's a total of 16 carbon atoms. When I count hydrogens on the left, there's a coefficient of 2 times 16. Oh, Linda. That's an 18, sorry. I had 36 in my mind. And for oxygen, the coefficient of 25 times the 2 atoms in each molecule gives us 50 oxygens. 16 carbons, 36 hydrogens, and 25 times 2 is 50 oxygens. Let's count the right side. For carbon, the coefficient of 16, and that molecule carbon dioxide just has 1 carbon in it, so there's 16 carbons. For the oxygen, just because it's in next, we have 16 times 2 from the carbon dioxide plus 18 times 1 from the water. 32 plus 18, oh, that's 50. 50 oxygens on the right side as well. Let's do the hydrogens next. Looks like there's 18 waters. Each of those has 2 hydrogens, so that's 36 hydrogens. We are indeed balanced. Same number of each atom on both sides of the arrow. Perfect. Let's look at letter C. Reading this out, we have sodium phosphate. Hear that name of the polyatomic ion chart? Sodium phosphate reacts with magnesium chloride. Every time I can practice nomenclature, I will, because it's important skill to keep practicing. Now on the product side, I see magnesium phosphate, PO4 is the polyatomic ion called phosphate, and sodium chloride. Now there was a reason I wrote all of that out, and I hope you are as well. Sodium phosphate reacts with magnesium chloride to form magnesium phosphate and sodium chloride. What I'm seeing here is the pattern of chemical change we will learn is called a double replacement, the double displacement, a double exchange. All of those are the correct category. You'll hear me call it a double replacement. See the 2 positive ions, sodium and magnesium? When I bring my eyes to the 4 characters here, I have a sodium connected to a phosphate, magnesium connected to a chloride. What happens is the 2 positive ions exchange partners. Magnesium now goes with phosphate, and sodium, oops, he should have been blue. And then sodium, who I color-coded yellow, went to the chloride. A double exchange. The sodium goes to the other partner's last name, chloride. Magnesium will go to phosphate. Sodium goes to chloride. magnesium goes to phosphate. And we'll consider charges when we practice this double replacement pattern as we predict out new formulas. And it'll double exchange, the two positives exchange partners. But right now, as I seed the next lesson with practicing, right now we're practicing counting. Alrighty, so letter C, let's count. We have a left and a right side. There's 4 characters really. We're going to count sodiums. We'll count individual phosphorus and oxygens. We'll count magnesium, and we'll count chloride. And I'm going to change my mind, and I'm going to show you why. I'm going to leave the polyatomic ion phosphate as a group. And this is a great trick when you're learning to balance equation. Because I can see on the left side phosphate, I can see it on the right side phosphate, that group of atoms acting as a unit, carrying a charge. Let's just leave it as a unit. So the number of sodiums, I can see there's a coefficient of 2, and there's 3 of them in there, so 2 times 3 gives me 6 sodiums. When I have a coefficient of 2, it talks through the whole compound, so 2 groups of phosphate as well. There's 1 unit of phosphate, but there's 2 sodium phosphates for a total of 2 PO4s. On the other reactant, we have MgCl2, so 3 times 1 gives me 3 magnesiums, and 3 times 2 gives me 6 chlorines. On the opposite side of the arrow, I can count 3 magnesiums, that's balanced, 3 on both sides. I can count 2 groups of PO4, that's balanced. Notice this PO4 is taken twice, so that's 2 units of PO4. Coefficient here is 6 for the NAs, that's balanced. And 6 times 1 is 6 chlorides, and that's also balanced. We've proved that each one of those obeys the law of conservation of mass. And so I'm proud of you for counting. It might seem so easy, or it just depends on the number of background practices you've had, how easy or how difficult this skill is. And so if I'm over teaching, I'd rather do that than assume we know. So the big skill of this very first practice is to just make sure you understand what the coefficient is doing to the equation. If a term has a balanced equation, it has a coefficient of 3 in front of the formula, Al2SO4 taken 3 times. This is called aluminum sulfate. Aluminum has a fixed charge of +3. Sulfate is a -2. So you can see when they crisscrossed, we had Al2SO4 taken 3 times. Aluminum sulfate. How many of each element do we have? Well, I have an aluminum, I have a sulfur, and I have an oxygen. If I were going to balance, I would probably leave the sulfates together. If on the product side, they're all together as well. Now, aluminum, there's 3 molecules, and each one of those molecules has 2 in it, so that's a total of 6. There are 3 molecules. Notice that the sulfur has just a coefficient of 1, but it's taken 3 times. It's like writing sulfate 3 times. So what if you had 3 SO4s? What does that mean, that coefficient? Times. 3 groups of SO4. That's what this means. Now the coefficient of 3 says you have 3 sets of those. So that would be 2 sets. And here's 3 sets of SO4. The coefficient of 3 and the subscript of 3 are both taking account to tell us there are 9. 3 times 3 is 9 sulfurs. How many oxygens? Well, count how many oxygens there are, and you'll see 1, 2, 3, 4, 5, 6, 7, 8, 9 groups of sulfate, and each one of those has 4 oxygens in it. So to kind of calculate that, you'd have 3 groups. Each one has 4 oxygens, and they're taken 3 times. 12 times 3 is 36 oxygen atoms. So what this tells us, the coefficient of 3, and this would tell us the parenthesis taken 3 times. Three units of aluminum sulfide contain 6 atoms of aluminum, 9 atoms of sulfur, and 36 atoms of oxygen. We have to be able to distribute the coefficient, knowing that the parenthesis says taken 3 times, meaning that you're writing out sulfate 3 times for each aluminum sulfate. And then 3 of those multiplies it again by 3. This is very challenging, so it requires practice. Keep practicing counting atoms. You know, we have some other chemical symbols that we can place into our chemical sentences just to kind of give them even more flavor. So for instance, if I'm writing a chemical equation and I come across an arrow from left to right, you know that that means it's a reaction arrow. If you see an arrow with a triangle on top of it, you'll know that that reaction is being heated. In order to decompose compound AB, you might need to heat it. So you'll see a triangle across the top of the arrow. The solid, liquid, gas, and aqueous phase are additional adjectives that you can place next to these symbols to let you know the phase of matter. If something is dissolved in water, it's an aqueous solution. So if I have, let's say, table salt as an S or table salt as an AQ, you now get a better feel of how the conditions are for the equation. This, of course, would be in a solid form. Just think of little salt crystals coming out of your salt shaker. A solid form of sodium chloride, where you have a very three-dimensional crystalline structure. But table salt also dissolves in water. So this would be salt water in a solution. So now you know it's occurring in water. Salt water, NaCl, AQ. We've done really good work. I'm going to stop the video here. You're going to come back and we're going to practice some balancing equations. We've made it through 1, and I mean that sincerely. We have 9 sections to make it through. Each one of these is very, very practiced. It's requiring a practice skill. So I'm going to encourage you to take little breaks, practice this, come back when you're ready to practice balancing equations with me.